Imagine a place where motion nearly disappears. Atoms slow to a crawl, light behaves in unfamiliar ways, and the rules that govern everyday physics begin to bend. This is not science fiction or fantasy. This is absolute zero, the coldest limit nature allows, a boundary where matter reveals some of its most extreme and surprising behaviors. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today, we are exploring what happens at absolute zero, the theoretical point where temperature reaches its lowest possible value and the familiar world of heat gives way to quantum reality. The idea of absolute zero began as a simple observation. In the early 18th century, scientists studying gases noticed that as temperature decreased, gases consistently shrank in volume. In 1702, French physicist Guillaume Amontons recognized that if this trend continued indefinitely, a gas would eventually contract to nothing. Though this state could not be reached, the implication was profound. Temperature seemed to have a lower limit. In the 19th century, William Thomson, later known as Lord Kelvin, formalized this concept by defining an absolute temperature scale. On this scale, 0 Kelvin represented the point where thermal energy reached its minimum. This temperature corresponds to minus 273.15 degrees Celsius. Temperature is not a substance, but a measure of motion. In solids, atoms vibrate around fixed positions. In liquids, they slide past one another. In gases, they move freely and rapidly through space. Cooling a material slows this motion. Absolute zero represents the theoretical limit where thermal motion is minimized as much as the laws of physics allow. Importantly, motion never fully disappears. Quantum mechanics forbids complete stillness. Even at 0 Kelvin, particles retain zero-point energy, a subtle residual motion required by the uncertainty principle described by Werner Heisenberg in 1927. For decades, absolute zero remained a theoretical boundary beyond experimental reach. That changed in 1908 when Dutch physicist Heike Kamerlingh-Onnes, working at Leiden University in the Netherlands, successfully liquefied helium. Helium resists liquefaction more than any other element, remaining gaseous until extremely low temperatures. By cooling helium to just over 4 Kelvin, Onnes opened the door to a new field known as low-temperature physics. 3 years later, in 1911, he observed something extraordinary. Mercury cooled below 4.2 Kelvin lost all electrical resistance. Electric current flowed through it indefinitely without energy loss. This phenomenon became known as superconductivity. Superconductivity revealed that near absolute zero, matter can enter entirely new phases that have no counterpart at everyday temperatures. In a superconductor, electrons pair up into quantum-linked units called Cooper pairs, allowing them to move through a crystal lattice without scattering. At higher temperatures, atomic vibrations disrupt these pairs. Near absolute zero, those vibrations fade, and quantum behavior emerges on a macroscopic scale. An equally strange transformation occurs in certain liquids. In 1937, Piotr Kapitsa in Moscow, and independently, John Allen and Don Misener in Cambridge, observed that liquid helium, when cooled below 217 Kelvin, behaved in ways that defied classical physics. It flowed without viscosity, climbed container walls, and seeped through microscopic cracks that should have confined it. This phase became known as a superfluid. Like superconductivity, superfluidity arises when quantum effects dominate the collective behavior of particles. As experimental techniques advanced, scientists pushed closer to absolute zero than ever before. In the late 20th century, laser cooling transformed atomic physics. By firing precisely tuned laser beams at atoms, researchers could slow them through repeated photon interactions. Using this method, gases were cooled to millionths and then billionths of a Kelvin above absolute zero. In 1995, Eric Cornell and Carl Wieman at the University of Colorado created the first Bose-Einstein condensate in a cloud of rubidium atoms. This exotic state had been predicted decades earlier by Satyendra Nath Bose and Albert Einstein. In a Bose-Einstein condensate, individual atoms lose their separate identities and collapse into a single quantum wave function. The entire cloud behaves as one coherent entity, displaying wave interference patterns visible at macroscopic scales. This state does not represent frozen matter. Instead, it represents matter in its most purely quantum form. Absolute zero acts as the gateway to this regime, even though it can never be fully reached. The reason lies in the third law of thermodynamics. As a system approaches 0 Kelvin, removing additional heat becomes increasingly difficult. Each step requires more effort than the last. Reaching absolute zero would require infinite steps or infinite time. Entropy approaches a minimum, but never reaches zero. Absolute zero is therefore not a destination, but a limit that cannot be crossed. Despite this, approaching absolute zero has reshaped modern science and technology. Superconducting magnets cooled with liquid helium are essential to MRI scanners, particle accelerators such as the Large Hadron Collider at CERN, and experimental fusion reactors. Atomic clocks rely on ultra-cold atoms to measure time with extraordinary precision. Quantum computers operate in cryogenic environments to preserve delicate quantum states that would be destroyed by thermal noise. Absolute zero also provides insight into the universe itself. The coldest regions of interstellar space hover just a few degrees above this limit. Vast molecular clouds, where stars are born, exist in these frigid conditions. The cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, fills the universe with radiation at a temperature of about 2.7 Kelvin. This faint glow is the leftover heat from the Big Bang, a snapshot of the universe when it was just 380,000 years old. Yet even at these extreme temperatures, the universe is not still. Quantum fluctuations ripple through empty space. Particles briefly appear and vanish. Absolute zero does not silence reality. It reveals its most fundamental activity. At its core, absolute zero teaches us that cold is not simply the absence of heat. It is a boundary where classical intuition fails and quantum laws take control. As matter cools, it does not freeze into lifeless stillness. Instead, it transforms, unlocking hidden phases, unexpected forces, and deeper truths about how nature is built. At the coldest edge of temperature, the universe does not fall silent. It whispers its deepest secrets. This is Mattermosaic, piecing together the universe, one discovery at a time. If exploring the coldest limit of reality changed how you think about motion, matter, and the laws that shape existence, share this story with someone curious about the extremes of physics. Let us know which fundamental boundary you want to uncover next, and subscribe for more weekly journeys across the fabric of reality.